Welcome to all of you in the next lecture of this course. Let us summarize what we have done in the last lecture. In the last lecture, we were trying to define a wavelet mathematically, because it is not like that if I give you a function and you satisfy those two properties which I have stated in my last lecture, say that, and based on that you call it as a wavelet, or vice versa. You give me a sum function, I try to satisfy those two properties and I call that as a wavelet. It is not that way, because there are some other properties also which are desirable. So, based on that, how we could construct wavelet mathematically, that was the idea behind last lecture, or not exactly last lecture, part of it. And this idea was given by two scientists, Stephen Mallet and Weissmeyer, which I have already stated in my previous lecture. And they are the scientists who discovered the theory, and that is the heart of wavelet theory, and that is called multi-resolution analysis, or in a short form it is called MRA. MRA, multi-resolution analysis. Okay. So, as I said that multi-resolution analysis is explained with the help of two spaces Vj and Wj. So, first we are concentrating on space Vj. So, for that reason I am saying multi-resolution approximation spaces Vj, they are closed subspaces of L2 R which satisfy the following axioms. Okay. In fact, we are calling it as a multi-resolution Vj. These are also called scaling spaces. This is also called scaling spaces. Okay. Why it is called scaling spaces, that I will define it later. So, now let us, whatever we have done in the last lecture, let us summarize all that into the form of axioms. So, the first axioms are Vj is subspace of Vj plus 1. Okay. Not this equality sign is not there, this is just this subspace. So, it means this is called that spaces Vj's are nested. Okay. This is the first axiom of the MRA. You can also call it as a M1. In literature many times it is called M1. Another second axiom of MRA is union of Vj, where J belongs to Z is equal to L to R. This is called completeness property. Completeness property, and this is corresponds to M2. Okay. The third axiom is phi x minus k, k belongs to Z, gives you an orthonormal basis for V naught. Okay. So, this corresponds to M3. Okay. And the fourth and last axiom of the MRA is, which I have already stated, if function belongs to Vj, its dilated element will belongs to space Vj plus 1 for j belongs to Z. This is called invariance to translation. So, if you look at any book of wavelet, this is a heart of the wavelet theory, and any lecture or any book on wavelet is incomplete without these 4 axioms. So, the last one is called M4. Okay. M1, M2, these are the 4 axioms which are satisfied by the space Vj. The first of these are Vj's are nested, completeness, and phi x minus k gives you an orthonormal basis. So, the concept which I have given you initially, translation, they are here, that if phi belongs to V0, translated elements will also be in the same space. Invariance to translation properties invoked here. The next is this invariance to dilations I have already stated. So, I do not need to again say. So, now you should have a clear idea how what are these Vj spaces will be. Okay. So, of course, the one of the assumption which I have stated in my intersection of Vj is a null set, that you could conclude from these 4 axioms. So, that is why I am not including that as a separate axioms, that intersection of Vj is a null set. Okay. So, and this phi which we are writing here, phi x minus k gives you an orthonormal basis for V naught. So, this phi x is called, phi x will also belongs to space V0, okay, and this is called scaling function. This is called scaling function, clear? And then phi x minus k, k belongs to z, will give you an orthonormal basis for space V naught. So, with the help of MRA, we are constructing one of the scaling functions initially. So, if now I use the nestedness property, V naught is subspace of V1. So, if the phi 2x minus k, k belongs to z, these elements you will have in V1. If you look at invariance to dilation property, and here I am also multiplying this with under root 2, so that I can define an orthonormal basis. So, basically phi x minus k gives you an orthonormal basis for V naught, as we have seen in the M3 axioms, and if I dilate that with 2, of course, this I am multiplying so that I can give you an orthonormal basis, it belongs to V1. So, this will be an orthonormal basis for a space V1, will be orthonormal basis for V1. Okay. So, if that is the case, I can write down phi x will also be a V1 from this property. So, I can write down phi x is summation of hk phi under root 2 phi 2x minus k, okay, where k is minus infinitive to infinitive. Okay. This is called dilation equation, or what you can call it as a, because here you say that we are connecting two different levels, V0 to V1. This was belonging to V0 and this was belonging to V1, and with the nestedness property we have connected this. So, this is also called two scale relation, two scale relation, dilation equations two scale relation, because it connects the phi at two different levels. So, now you could yourself appreciate what are the beauty of MRA axioms. Okay. Clear to everyone? And this HKs are called low pass filter coefficient, low pass filter coefficients. Okay. HKs are called low pass filter coefficients. Now, if I am giving a one of the example that okay, phi x is given by this 1 0 if x is, otherwise it is 0. So, how the translation and dilations will behave with respect to this function, that I am showing you with the help of figures as well. So, this is phi x, okay. 0 to 1 it is 1, rest it is 0. How the figure will look like of phi x. This is a very simple box kind of a function. So, how the translation will affect, that I am showing you now. So, phi, so this is phi x minus 1, it is translated by 1, that is why it is from 1 to 2, translation by 1, it has shifted from here to here, that is how the translation will behave. Again, now I am also showing you the effect of dilation, phi 2x. So, if I am dilating, the width will be half. So, this is 0 to half, okay. So, that is the function. Let me again reopen phi 2x, okay. Next thing, how when I will translate this phi 2x, how it will look like, phi, that will be phi 2x minus 1. So, that also let me show you graphically. Phi 2x minus 1. So, with the help of a one example, I have shown you what will be the effect of dilation and translation. Now, you have to observe these figures more carefully to conclude how I can write down phi x in the form of phi 2x and phi 2x minus 1. Because if you look at phi 2x minus 1 was shifted from half to 1, this was 0 to half and phi x was 0 to 1. So, if you look at all these 4 figures carefully, which I have shown you here, I can write down this relation, phi x is equal to phi 2x plus phi 2x minus 1. Okay. I can observe this graphically as well. If I wanted to derive this mathematically, I can conclude from here. Okay. So, what will be the conclusion? So, of course, then H naught will be, I can H naught will be, because for k is equal to, this corresponds to k is equal to 0, this corresponds to k is equal to 1. So, k is equal, if k is equal to 0, this will be H naught, under root 2 is there. So, I am taking 1 by under root 2 and H1 will also be 1 by under root 2. Okay. But okay, so that is how we can construct, and this phi x is called, is one of the major disadvantage of this wavelet is, I am going to say one of the major disadvantages, that this phi every time you do not have an analytical form. Analytic form means closed form, means I cannot tell you that phi x will be like a sin x function or the expression of phi x will be this. No, I cannot say you. So, that is one of the drawback of the wavelet, you could call. Okay. So, that is why here how to construct a phi itself is a non-trivial task, and then how we will construct this phi if we do not have an analytic expression, that I will come to the later point, because this was a very simple example I have written, but how to construct this, that's altogether different game. Okay. So, these of course, so in this case it will be called compactly supported scaling function, because only for finitely value of k, hk's are non-zero, otherwise they are 0. Okay. So, later on I will based on this compactly supported scaling function, I will also define compactly supported wavelet. Okay. So, that is the idea. Now, in the same way, if I wanted to generalize this scaling relations, I can connect any two scaling functions at the different levels. So, now what will be the basis of space Vj? The basis of this space will be again k belongs to Z. This will be an orthonormal basis for space Vj. I have started with phi, I am keep dilating phi 2, phi 2x will belongs to V1, so phi 2 to the power jx will belongs to space Vj, and I am multiplying this with this factor which I have already explained, because so that it gives you an orthonormal basis. So, based on this invariance to dilation nestedness property, I can conclude that this will be an orthonormal basis for space Vj. Okay. So, now the next issue comes, what should I do to move from Vj to Vj plus 1? What should I do? Okay. So, of course, I will be adding some information in space Vj to achieve this space Vj plus 1. Okay. So, for that and for that reason I am defining another space Wj in the following manner, okay, such that this direct sum, other things I have already explained, so I do not need to re-explain again. So, this is the first time I am bringing this space Wj. Okay. As I said, Vj's are called scaling spaces and Wj are called wavelet spaces. So, if you look at more carefully, you can call it that multi-resolution analysis is explained with the help of two spaces, Vj and Wj. Vj's are scaling spaces, Wj's are called wavelet spaces. Okay. So, now that is how we are defining Wj. So, if you can recursively use this Vj plus 1, again Vj minus 1 plus Wj minus 1 Wj. Okay. So, you can keep iterating this procedure. So, finally, if I wanted to say this will be, I can say V j0 plus j is equal to j0 to j minus 1 Wj. Okay, clear? So, this is Vj plus 1. So, here I have again used recursive Vj minus 1 Wj minus 1 plus Wj. So, this is j to j0 minus 1. So, j0 is called coarsest level of approximation and j is called finest level of approximation. So, that is j0 is coarsest level of approximation and j is finest level of approximation. Okay. So, this is the idea we are using. So, that is how if there is any function, that is how we can divide that information at different levels. So, each Vj has some information about the function, each Vj at different scales, and if capital J tends to infinitive, basically you could call it as a okay, you can. So, this is the main. As capital J also tends to infinitive and J0 tends to minus infinity. So, now I will tell you basically V1 is V0 plus W0. Okay. So, how this when we are moving from a space V0 to V1, this will play a role. So, that is the place where this wavelet spaces are coming into the picture. So, for that I am going to explain with the help of figure. Okay. So, that is you could see if minus phi x belongs to V0 and psi x belongs to. So, how you could, so basically I wanted to connect three different spaces V0, V1 and W0. Okay. So, basically you could see I can write psi x minus phi x is equal to 2 phi, 2x belongs to V1. So, with this relation psi x minus phi x is equal to 2 phi 2x, I am moving into the space V1. So, in a nutshell or in a short form, how we define? We define psi x will be a function which will belongs to space W0 such that psi x minus k, k belongs to z will also be an orthonormal basis for a space W0. And again if I use this dilation property 2 to the power j by 2 psi 2j x minus k, k belongs to z will be an orthonormal basis for a space W j. Okay. So, this will be an orthonormal basis for a space W j. So, if you every wavelet system is characterized by two functions. Every wavelet system is characterized by two functions, phi and psi. The way I was saying that multi-resolution analysis is explained with the help of two spaces Vj and Wj. Same way every wavelet system is characterized by two things. I should not call it every wavelet system, I should call it this every word should be replaced by mostly, okay, or every in that sense whatever wavelets we are constructing with the help of a MRA, in that sense this every word will be there. So, every wavelet system is characterized by phi and psi if it is constructed using MRA. Okay. So, now it should be clear to you, and this phi is called scaling function. And psi is called wavelet function. Okay. So, basically we are calling, when we are defining wavelet using MRA, first we construct phi and then we construct psi, and as I said psi x belongs to W net, which is again a subset of V1. So, this is with the this property if you look at. So, I can write psi x as a linear combination of the basis element of V1. What are the basis element of V1? We have already seen under root 2 phi 2x minus k, k belongs to Z will be an orthonormal basis for a space V1. So, that is why with that concept I am writing this as a this. Okay. So, where GKs are called high pass filter coefficient. Filter coefficient, and this is called wavelet equation or two scale relation for wavelet. Like previously we have seen, if you look at more carefully, this we have seen which was called dilation equation and two scale relation for scaling function, because phi is scaling function. When we are writing psi in terms of phi, then we are calling two scale relation for wavelet. HKs are low pass, GKs are high pass. So, there is a very much similarity between the dilation equation and wavelet equations, and corresponds to this we define this low pass and high pass filter coefficients. Okay. HKs and GKs are low pass and high pass filter coefficients. So, I have already given you one example of phi x box function. So, with the help of that function, can you construct a wavelet psi x? Yes. So, I am giving you one example of psi x, which will be 1 if minus 1 if it is half, 0 otherwise. Okay. So, if this is the psi x, because if you look at this is the kind of example I have given you initially also, because it satisfies both the basic property, it is a localized function as well as integral of psi x dx will be 0. But now the question comes up, how I can write this psi x in the form of phi x, okay, which I have already stated as a box function. So, for that reason you could also observe a figure, or you could write down phi psi x will be phi 2x minus phi 2x minus 1. Okay. For that reason you could observe the figures which I have shown you for phi 2x and phi 2x minus 1, then it will, you will get this. So, basically if you look at now this wavelet equations carefully, G naught will be this and G1 will be this. Okay. So, again I am saying in this case also GKs are non-zero only for finitely many k's, means only for k is equal to 0 and 1. That is why it is called compactly supported wavelet. It is not that every wavelet is compactly supported. I have never made a statement that wavelet will be a compactly supported functions. Okay. Wavelet can be compactly supported, and if it is a compactly supported function, it is a plus point. So, to observe this dilation and translation with respect to this psi function, I am showing you the figures. So, you look at psi x, okay. Everyone can observe how the psi x will look like. So, this is 1 between 0 to half, half to 1, this is minus 1. Okay. This is the graphical representation of a psi x function which I have shown you. Now, if this is the psi x, with respect to translation, how it will look like? Okay, so this will be the psi x minus 1. So, it is translated by 1. Earlier it was supported in 0 to 1, now it is supported in 1 and 2. Okay. So, this is the translation effect. Dilation effect you will see now. So, this is dilation means support is, this is squeezed. So, this is you could see from here, earlier it was supported in 0 to 1, now it is supported in 0 to half. Okay. This is psi 2x, and again if I translate this psi 2x, effect will be this. So, again it is shifted. Okay. So, that's how one could observe the dilation and translation effect of phi and psi with the help of different figures. Okay. So, now by this time you must have a knowledge of how to construct phi and psi with basic properties. Okay, with basic properties. Now, I am going to define another important property of the wavelet which every wavelet should have, and why it is important, that I will define anyway, and that property is called vanishing moment. Okay. So, the basic idea of this property is as follows. A wavelet has m vanishing moments if corresponding scaling function can represent polynomials of degree m minus 1 exactly. Okay. So, what is the mathematical way of writing this? A wavelet has m vanishing moment if and only if corresponding scaling function can represents polynomial of degree m minus. So, p, where p is polynomial of degree m minus 1 up to m minus 1 exactly. Okay, up to m minus 1 exactly. So, this I am writing with this. Okay. So, this is just a mathematical representation of the same thing which I have said. So, here to write down the polynomials of degree m minus 1, I do not need any wavelet term, and that is why that vanishing means wavelet coefficients are vanished. That is the meaning of vanishing term, and MLP is basically xp phi x minus L dx, and this is called moments of the scaling function, which will be subsequently used for some calculations. Okay. But most of the time this property which we call it as a wavelet has m vanishing moment property is given to you in an alternate fashion, and what is that alternate fashion? I am driving that fashion. So, if you integrate this expression star with psi x, okay, MLP integral of phi x minus L psi x dx. So, because phi and psi are orthogonal, so this will be 0. So, basically this is equal to 0 for p is 0 1 to m minus 1 property. So, this is the property most of the time we call it as a M vanishing moment property, which is basically constructed from here, that when scaling functions can represent exactly polynomial of degree up to m minus 1. Okay. Or alternate way of doing the same thing is, of course, this integral is over r minus infinitive to infinitive. So, if my question to you is, whatever psi x I have given you the example, like this was 1 in 0 to half and minus 1 in half to 1. So, what will be the vanishing moment for that psi x? Because in that psi x we can say integral of psi x dx is 0. Okay. So, that will have a vanishing moment m, because it has a m vanishing moment if it is satisfying up to m minus 1. So, if m is 1, p is 0 and integral of psi x dx is 0, which we can observe. Okay. So, the wavelet which I have shown you earlier has only one vanishing moment. Now, okay, this is one of the property I have stated, but why I am stating that? It has many advantages, and because I should not say it has many advantages, because of this wavelet have many advantages, I should say in that manner. Because how it helps the wavelet, this is the property which helps the wavelet in any domain. Either you could call it in the form of a compression for engineers, or producing a adaptive grid if someone wants to take the application of wavelet to a differential equations, or in any other way. Okay. Compression, signal compression, image compressions, helping detecting in the singularity, in any way. This is the property, because of that wavelet has plus point, and wavelets are so powerful, you could say. Okay. So, this is very important property of the wavelet, and it is called vanishing moment. Later on I will explain also how it helps in detecting the singularity of a function, or one could observe that, because very much that this property is not posed by Fourier basis function. Okay. Now, let me give you one, because so far you have seen, okay, I have given you, in any case I am giving you one example, because we have seen many property of the multi-resolution approximation spaces. So, I am giving you one example where you could see that which property is violated, so that it does not form a multi-resolution approximation spaces. Which multi-resolution requirements are violated if Vj consists of all trigonometric polynomials of degree less than j. Because what we have seen so far, we have seen MRA, and then I have also stated one of the very important property of wavelet, which is called vanishing moments. And now I am giving you one of the example where which multi-resolution requirements are violated if Vj consists of all trigonometric polynomial of degree j. So, can you think how to tackle these examples, or which M1, because which of the multi-resolution requirement means M1, M2, M3, M4, which one is not satisfied? Because think for a while, otherwise let us say V0 sin x trigonometric, sin x is a trigonometric polynomial. So, sin x will be V1, trigonometric polynomial of degree j. Okay. So, if I dilate it with 2 sin 2x, it should be V2. Okay. So, if you look at this expression of sin 2x, this is 2 sin x into cosine x. So, it has a degree 2, that is okay. Up to V2 it was fine, but sin 2 to the power 2 x, because that is what I am using the dilation property, it should go into the space V3. Okay. But this is, what is this? This is sin 4x, sin 4x is equal to 2 sin 2x into cos 2x, but here it will not be contained in V3 because it is a just this is sin x. Okay. Okay. So, but what is the degree of this polynomial? Degree of this polynomial is 4. So, according to the MRA it should be in V3, but it is not in V3. Okay. So, this is means dilation property is violated, means when I am dilating it is not going into the next space. So, that is why this will not be in V3. So, this is the property which is violated. So, I have also given you one example where you could see that if Vj's are spaces which contains trigonometric polynomial of degree less than equal to j, it will not satisfy M3 axioms of the MRA, that is why it does not form a MRA. So, it is not that you can say everything is a scaling function, wavelet function of Vj and Wj. Vj are the approximation spaces which satisfy certain axioms, only then corresponds to V naught if there is a one element which generates the whole space V naught by translation, then phi is called a scaling functions. Okay. So, now the next question comes, this is example we have already done. So, now the next question comes, if phi x is given in the following form. Okay. Okay. This is what we have concluded from MRA, 2 scale relation for phi, 2 scale relation for psi, dilation equation, wavelet equations. Okay. How to construct this phi and psi if they are not given analytically? Okay. If they are not given analytically, how to construct? That is my next question, and that is the non-trivial to answer, and because of that there is a mathematical construction behind it, that the construction of this boil down to the problem of a linear algebra, because phi is connected at two different space. So, I can initially I will compute phi and then recursively I will compute. So, that is how it will be a problem of linear algebra. Okay. So, now basically the next topic will be evaluation of scaling functions and wavelets. Why I am saying evaluation of scaling function and wavelets? Because they are not in the form of a closed form expressions. We have to compute them. So, how to compute them itself is a non-trivial task. Okay. And because of that wavelets are not many engineers are not very comfortable to use it. But nowadays there are many inbuilt MATLAB routines are also there, how to compute phi x and psi x. There are 3 popular methods for computing phi x and psi x, and 3 popular methods are like that: cascade method, spectral method, and recursion method. Okay. So, I will explain each one of them in briefly in the next lecture, but before that let me give you an idea. Cascade, as all of you know, what is the idea behind cascade? That iteratively we are using the same thing. So, that is will be the idea behind using cascade method. Spectral method will be based on the Fourier transform, and recursion method will be like it will be a boil down to the linear algebra, how we are recursively using it. There is also inbuilt MATLAB routine for computing the value of phi x and psi x, and that inbuilt MATLAB function uses which method, that I will also tell you in my next lecture. So, before that you could think yourself little bit, how if psi x is unknown, phi x is unknown, and that is available in the left hand and right hand side both, how we can compute them, how we can compute them. Okay. The methods which are used in the literature for computing them are these three. These methods I will explain in my next lecture. So, thank you very much.